My name is Edson Kofi. I'm happy to present this poster on behalf of the Uprise Consortium for this webinar showcasing science in action. I am currently in Ghent as a PhD student visiting from a University of Abomey-Calavi. I am working on food safety and mycotoxin risk assessment in cereal-based foods across Africa as part of the Uprise project. This work focuses on mycotoxin contamination in cereals and fermented foods across 5 African countries between 2014 and 2024. As you know, mycotoxins are toxic substances produced by fungi such as Aspergillus, Fusarium, and Penicillium, and they are a major threat to food safety in Africa, particularly in staple crops like maize, sorghum, and millet. Since this poster contains a lot of detailed information, I will focus on presenting just the key highlights and main findings to give you a clear overview within the limited time we have. This study was conducted as part of the EU-funded Uprise project and aimed to map mycotoxin contamination in cereals, fermented foods, feeds, and milk. Cover 5 countries: Benin, Côte d'Ivoire, Nigeria, Kenya, and South Africa, each representing a different African region. Analyze 63 scientific studies published between 2014 and 2024, extended to 2011 in the case of Benin due to limited data. The review focused on major mycotoxins: aflatoxins, fumonizins, ochratoxin A, deoxynivalenol, and zearalenone. We analyzed contamination in maize, which is the most studied crop, fermented foods and beverages, such as ogi, maou, pito, burkut, and mersik, as well as milk in Kenya and feeds in South Africa. The detection methods varied. We have advanced tools like LC-MS, MS, were common in Nigeria and South Africa. Simpler tests like ELISA or stripe-based methods were used in Kenya and Benin. About the key findings, we have across countries, Nigeria and Kenya had the highest level of contamination, especially in maize. Côte d'Ivoire had significant levels of ochratoxin A, deoxynivalenol, and zearalenone in cereals. In Benin, data were scarce but showed contamination in maize and some fermented foods. In South Africa, high levels of fumonizin were found in maize and animal feed. Fermented products, although less studied, also showed traces of contamination, highlighting the need to better understand how traditional processing affects toxin levels. In conclusion, we can say that mycotoxin contamination remains widespread and poorly controlled in many African food systems. And there is an urgent need for stronger monitoring systems, affordable detection tools, and better integration of food safety into national policies. Within the Uprise project, we aim to combine this review with climate and farming data to understand contamination risks and support more targeted food safety strategies. We are at the end of our presentation. Thank you very much for your attention. We are happy to receive your question.
Hello, everyone. My name is Mahdi Mohammed, and I'm a PhD student from Wageningen University in the Kingdom of Netherlands. Happy World Food Safety Day. Today, I'm going to talk about my poster on mycotoxins and predictive models in Africa. Now, some background on my studies. Africa is a major producer, consumer, and trader of cereals. It faces significant challenges due to mycotoxin contamination. Now, what are these mycotoxins? Mycotoxins, of course, are fungal metabolites primarily produced by Aspergillus and Fusarium species, and it poses serious threats to food safety, security, and public health. Factors such as geolocation, climate uncertainties, and socioeconomic disadvantages exacerbate the problem, particularly affecting small-scale farmers. Now, despite ongoing efforts to develop diagnostic, monitoring, and management tools for mycotoxin control in Africa, many studies have proven to be labor-intensive and cost-prohibitive. Therefore, predictive modeling has emerged as a potential solution for successful applications in developed countries, and of course, some adaptations for African context. Objectives of my studies include, number one, to identify frequently used models, data sources, and key predictive variables. Two, to evaluate model accuracy in different African regions. And three, and final one, is to propose strategies for real-time monitoring and early warning systems. Now, the methods we adopted is a systematic literature review by the Prisma model, where we reviewed articles published from 2014 to 2024 on machine learning-based and mechanistic predictive models for mycotoxin contamination in maize, millet, and sorghum during pre- and post-harvest stages in Africa. Metrics and model validation techniques are mainly R-square sensitivity and specificity. Now I have a figure below here, one representing data sources, and the other one that leads us to the results section, which is what we found out in our studies. The models utilize sampling and analytical results data, sometimes spectral and images data, with even an introduction of large language models for chatbot systems in Africa. Many studies leverage freely available climate and GIS data from FAO databases requiring rigorous pre-processing techniques. And key predicted variables include soil organic carbon content, soil water supply to demand ratio, pre-flowering NDVI, soil pH, and finally growing season length. Now, the second figure presenting the distribution of data sources, which highlighted some data sources or some data coming from the Famine Early Warning Systems Net Africa, some databases such as the HWSD from the Digital Soil Map of the World, and of course, others coming from animal sampling analytic techniques, the rapid tests, and so on. Now, in the next figure, just below it, is a figure that presents the model performances and comparisons. Now, the R-square, which measures the fitting of the model, while sensitivity and specificity measures the accuracy and model performances. In the R-square, how fitting the model is, random forest performed best from this figure. And based on this figure, you can see the 2 or 3 neural network models, the VGGI16, ResNet 152, and Inception V3 perform the best. Now, a disclaimer, this is a figure which shows some normalized model performances for each model across different studies. And we come to a conclusion that incorporating agronomic practices in modeling processes, combining historical and climate variables, could enhance prediction accuracy. Additionally, developing user-friendly mobile applications for real-time prediction and risk assessment for mycotoxin contamination in crops across African countries would improve accessibility and practical application of these models. Researchers should focus on expanding the scope to include multiple mycotoxins and crops, integrate diverse data sources, validating models for different African regions, establishing collaborative networks to share data and improve model accuracy. Now, this is the end of my presentation, and thank you all.
Hello, everyone. Thank you for being here today and for attending the Uprise presentations. My name is Julia Virol. I'm a PhD candidate affiliated with Wageningen and Ghent University. And today I'd like to present my work over the past year on my thesis. The thesis is focusing on incentivizing food safety in African traditional fermented food production, with a specific focus on informal entrepreneurs and intervention design. I think there's no need to explain the background further, that food safety is absolutely necessary to achieve food security. Still, every year, 862 million African people are food insecure, and 135 million are affected by foodborne diseases. Those diseases might lead to death. Foodborne deaths in Africa are majorly caused by biological and chemical hazards, and among those are aflatoxins. Aflatoxins among the mycotoxins that Uprise project is trying to limit. The positive thing is that researchers have found that those informal agri-food entrepreneurs and workers have the potential to improve African food systems, notably by producing safer food. So the informal sector is defined as neither regulated nor protected by the state. That means that it requires a specific approach to work together with these stakeholders. Why are they very important? They make up 90% of the African agricultural sector. And on the demand side, actually, it's a majority. I think more than 70% of the continent gets their food from informal markets. To unlock the potential of informal agri-food entrepreneurs, we need to better understand their motivations, organization, their context. There's still a lot to be learned. And that's why with my thesis, I investigate how to better characterize the stakeholders as a way to inform intervention design for safe food practices in sub-Saharan Africa. So this thesis will be drawing from several fields: food safety economics, development economics, behavioral economics, to pursue 4 different objectives. First, establishing the determinants of practices in the informal agri-food sector in sub-Saharan Africa. The second is to assess which determinants of informality are linked with the adoption or lack thereof of food safety practices. The third objective is to provide an ex-ante impact assessment of food safety interventions that would limit mycotoxin contamination along the value chain. So not just the food producer or the food seller, but all throughout. And finally, the last objective is to understand whether there are some gender-specific factors that might hinder or promote food safety. And the reason for that is because a lot of women might resort to agricultural food jobs for their livelihood, and they cannot be left behind. In order to work over these 4 objectives, I'll be first conducting a systematic review. Then I'll be moving on to more statistics with a multivariate analysis of informal entrepreneurs' capability, opportunity, and motivation to implement safe food practices. Then for the third objective, I'll be moving to some modeling techniques, most probably agent-based modeling. And finally, we'll be using some experimental methods. I'd like to just give you a peek view of what I'm doing at the moment. So the systematic review is an ongoing work. Using the PRISMA guidelines, I'll be systematically reviewing what drives production practices among informal agri-food entrepreneurs in sub-Saharan Africa. And the objective for that is because there is no specific literature on behavioral determinants on food safety, but there must be something to be learned from the critical mass of papers that we can find on adoption in general on the continent. Something that we expect is that we could be testing hypotheses that whether determinants of behavior can be linked either to a type of entrepreneur, to a specific type of behavior. Those are hypotheses that we will be testing. By the end of this review, what we're hoping to do is that we will be able to map the different determinants of behavior onto the COMBI, which is a model that was designed by Michi et al. In 2011. And basically, it breaks down a behavior into several components. And the very nice thing is that for our Uprise project, we're going to be able to use this very academic tool that has been linked to what is called the behavior change wheel. And the behavior change wheel allows you to understand, based on the main barrier to achieving a behavior, what would be the best intervention to put in place. This is for the systematic review. What we're also doing at the same time with my supervisors is already starting to plan the fieldwork. And for that, we want to understand the drivers of the implementation of safe food practices among Onkomboti processors in South Africa. And here, we're going to try to associate determinants of informality of those food processors and whether those determinants have an explanatory power over processors' capability, opportunity, and motivation to implement safer practices. I guess this is all for me now. I'd be happy to take on any question, and thank you again for listening.
Good day, everyone. My name is Favor Ayoride, a master's student at the University of Ibadan, also a research fellow at the International Institute of Tropical Agriculture, IITA, Ibadan, Nigeria, under the Healthy Diet for Africa project. I'll be presenting on safety assessment of bush mango seeds along its value chain. Bush mango is an underutilized crop that is mostly cultivated and consumed in some African countries, including Nigeria, Gabon, Guinea, and Cameroon. It consists of several species. However, the common species are Iveja gabonensis and Iveja wombulu. Here is a sample of Iveja gabonensis. The mesocarp and the seeds are edible, but only the seeds of Iveja wombulu are edible. Here is also a sample of how the seeds look like. In Nigeria, these seeds are used to make thickening soup known as ogbono, and that is what we can see in figure 1b. Presence of aflatoxin and pesticide residue in food has resulted in adverse health effects. It has also been reported in previous research that molds and mycotoxin are present in bush mango seeds. But the co-occurrence of aflatoxin and pesticide residue are yet to be studied, which is why this research was carried out. Samples were obtained from 3 states in southwest Nigeria, and the methods carried out were isolation of molds, extraction and quantification of aflatoxin, and lastly pesticide residue analysis. From the results obtained, 3 fungi genera were isolated, which are Aspergillus, and that's what we can see from figure 2a to d. We have Aspergillus flavus, Aspergillus niger, Aspergillus fumigatus, and Aspergillus tamari. Figure 2e shows Penicillium species, and figure 2f shows Rhizopus species. Figure 2g shows seeds that are contaminated by molds. However, it is to be noted that molds are not always visible on seeds sold in markets, which may be because of the drying process that has taken place, but this was taken during sampling. Also, Aspergillus flavus was predominant, and this is a microorganism of importance in aflatoxin contamination, hence the reason why aflatoxin analysis was carried out. Figure 4 shows the result of aflatoxin incidence in disease, and it was revealed that there was no presence of aflatoxin in fruiting sample. However, aflatoxin contamination was present from fermenting samples to market samples, with market sample from Ekiti State having the highest level of contamination, which may be because of the exposure of these seeds in market. Figure 6 shows the pesticide residue incidence, and it was revealed that all samples were contaminated with pesticide residue, and this can be as a result of misuse of pesticides by farmers and processors. Also, chlorpyrifos ethyl was prevalent across sampling points. However, emamectin benzoate was predominant in fermenting sample, and this could be as a result of fruits being left on the ground to ferment for days, thereby taking up pesticide residue from the soil. In conclusion, pesticide residue and aflatoxin are present in bush mango seeds. However, there is need for optimization of processing of this crop through proper handling and control on the use of pesticide by farmers and processors. I would like to acknowledge the European Union via the Healthy Diet for Africa for funding this project, and I would also like to acknowledge the International Institute of Tropical Agriculture for the research fellowship awarded to me and my colleague Busayo Olowolafe. Thank you.
Welcome everyone. My name is Felix Ondiek from Kenyatta University, Kenya. I'm a PhD student under the Healthy Diets for Africa project, and I would like to present to you my findings on a study I'm conducting on the levels of acrylamide in foods consumed by mothers and children aged 6 to 23 months in Makueni and Nairobi counties of Kenya. Thank you for your audience. Now, a brief introduction. I would first begin by saying that acrylamide is a chemical compound formed in starchy food products during high temperature cooking, like using cooking methods like frying, baking, and even roasting. And it can also form during industrial processing at high temperatures conditions above 120 degrees centigrade and low moisture. Now, the levels of acrylamide in foods can also be influenced by factors such as storage conditions, post-harvest handling, and genetic variation of food crops, because these factors usually will determine the levels of precursor compounds needed for the formation of acrylamide during cooking. And acrylamide mainly forms through Maillard reactions, which is a surface reaction. That one means it forms on the surface of foods during cooking. And usually the color of the food will be indicative of the levels of acrylamide in the food. Like darker colors will mean higher levels of acrylamide in the food. Now, the concern surrounding the presence of acrylamide in foods arises due to the fact that it has been classified by the International Agency for Research on Cancer as a probable human carcinogen, that is group 2B carcinogen. Now, exposure to acrylamide usually applies to the general population because it forms in foods that is consumed by the general population. But young children might be at a higher risk of exposure because of their tendency to snacking. And studies have reported that snack foods usually contain higher levels of this chemical. And children might also be at a higher risk of the effect of this chemical because of their relative smaller body weight mass. So in my study, my objective was to analyze the concentrations of acrylamide in foods commonly consumed by children aged 6 to 23 months and their mothers in the two counties, Makueni and Nairobi, And I'm also seeking to assess the levels of dietary exposure to acrylamide among the study population. Now, I have some of my findings with me, and from my findings, we can see that there are some foods that recorded high levels of this chemical, that is acrylamide. And some of those foods with high levels of acrylamide were bajia. Bajia, potato fritters, is a common and popular snack in Kenya. We also had potato chips recording high levels. Interesting, cakes also had high levels of acrylamide. And mandazi, another popular snack in Kenya, had high levels of acrylamide. For example, looking at bajia, acrylamide levels for food samples from Makueni County ranged between 226 and 626 micrograms per kilograms, with about 39% of samples recording levels above the benchmark levels. While in Nairobi, acrylamide levels in bajia samples ranged between 140 to 619 micrograms per kilograms, with about 46% of samples recording levels above the benchmark levels. Now, for potato chips, we have samples from Makueni County had acrylamide levels ranging between 332 to 688 micrograms per kilograms, with almost half of the samples recording levels above the benchmark levels. That is 48.1%. Now, for Nairobi, potato samples had acrylamide levels ranging between 244 to as high as 1,750 micrograms per kilograms, with 65% of samples recording levels above the benchmark levels. Now, for mandazi, we have samples from Makueni recording acrylamide levels between 214 to 956 micrograms per kilograms, with a quarter of the samples having acrylamide levels above the benchmark levels, while in Nairobi, samples for mandazi had acrylamide levels ranging between 163 and 468 micrograms per kilograms, with 3/4 of the samples recording levels beyond the benchmark levels. Now, for cakes, we find that, for example, Nairobi, we had samples recording as high concentrations as almost 2,000 micrograms per kilograms. Now, that is almost 5 times concentrations beyond the benchmark levels, and that one is very significant for safety. Now, for Nairobi, for Makueni samples, cakes had acrylamide levels ranging between 271 to 965 micrograms per kilograms, with 3/4 of samples recording acrylamide levels beyond the benchmark levels. Now, in a nutshell, in conclusion, we can see that from these findings that a number of foods contained acrylamide levels beyond the benchmark levels. And we also see that samples, high-risk food, a number of high-risk food with regard to acrylamide, for example, bajia, potato chips, mandazi, cakes, we see that they had a number of them having levels beyond the benchmark levels. Now, looking at these results, I don't observe any much variation in acrylamide levels between samples from the rural setting, that is Makueni, and samples from the urban setting, that is Nairobi. Now, in a conclusion, the recommendations that I would like to maybe make from these findings briefly, there is need to continue monitoring the levels of acrylamide in food consumed by different populations. And there is also need to create awareness regarding acrylamide in the food value chain, and possibly conduct education on cooking methods, safe cooking methods, and safe processing methods at different levels. For example, targeting the households, targeting food catering providers, and also targeting processing industries. And something that I'm going to take on in the next phase of this research will be to conduct exposure and health risk assessment to reveal the level of dietary exposure among the population and the health risk associated with it. So that's all for those brief findings.
Good day, everyone. My name is Taiwo Adeshino, a postgraduate student at the University of Ibadan, Nigeria, and a research fellow at the International Institute of Tropical Agriculture, IITA Ibadan, Nigeria, with the Healthy Diet for Africa project. My poster presentation answers the question, are urban and peri-urban West African households aware of food hazards, and does this influence their purchase pattern? Staples such as cereals, legumes, and fermented condiments are popular in West Africa. This is because these food groups provide energy, serve as a vital source of protein, and enhance the flavor of soups. However, these food groups can be contaminated with mycotoxins, heavy metals, and pesticide residue due to misuse of fertilizers, herbicides, and insecticides, as well as suboptimal processing and storage conditions. Health risks such as gastrointestinal disorder, immune suppression, growth impairment, and cancer can be caused by mycotoxins, heavy metals, and pesticide residue contamination in food. Hence, awareness is an important factor for limiting exposure to food hazards. This study therefore assessed the level of awareness among urban and peri-urban households, and data was obtained by administering questionnaires to adult respondents using the Kobo Collect app in 300 households, 100 households each in Benin, Ghana, and Nigeria. Results showed that 58% of Nigerian respondents lacked awareness of food hazards, while 53% of respondents from Benin lacked awareness of food hazards, and just 12% of respondents from Ghana lacked awareness of food hazards, as this is shown in figure 2. This indicates that across the three countries, level of awareness was low in Nigeria and Benin compared to Ghana. Also, 33% of Nigerian respondents indicated that awareness of food safety hazards does not influence their purchase pattern, while 10% from Ghana and 4% from Benin indicated likewise, and this is represented in figure 3. 51% of respondents from Nigeria reported that they store their food for 1 month before consumption. However, 48% from Benin and 73% from Ghana store up their food for up to 1 week before consumption. It is important to note that storage length can affect the quality of food depending on the storage conditions in households, especially in coastal regions where the study areas are located, which experiences high humidity, and high humidity can facilitate the growth of microorganisms that can lead to food deterioration. In conclusion, this study showed differences in food safety awareness across in conclusion, this study showed differences in food safety awareness and storage practices across the countries, with Nigerian respondents exhibiting lower sensitivity to contamination risk and longer storage duration. During my survey, this fact sheet was developed and given to household members just to increase their level of awareness about food hazards, and also some methods of preventing food hazards. This fact sheet was sponsored by the Healthy Diet for Africa project. I'd like to acknowledge the European Union for funding this research through the Healthy Diet for Africa project and the International Institute of Tropical Agriculture for the research fellowship awarded to me. Also, I'd like to acknowledge the IIT Biometrics Unit and the enumerators that assisted in data collection. Thank you.
Good morning, everybody. I am Abudu Azim Bolale, a PhD student at postgraduate school in agriculture and water science of National University of Agriculture in Benin Republic. I am going to present briefly a study focused on integrated strategies to reduce pesticide residues in cereal and legume grain in Benin Republic. Synthetic predators like cypermetrins, permetrins, and deltametrins are commonly found in the soils of cereal and legume fields. These insecticides are widely used in Nigeria and Benin Republic, often by illiterate or untrained farmers, which raises safety concerns of quality of foods. Moreover, mycotoxins, especially aflatoxins, phenolizins, and ochratoxin produced by fungi also contaminate these crops, posing serious risk to food safety and public health in this country. The main objective of this research is to identify pesticide and aflatoxin residues in intercrop maize and legume grains across Benin Republic. Specifically, we aim to understand farmers practices, to evaluate the health and environmental risks, and also promote better market access and food safety across Benin Republic. To achieve this goal, we need a good methods and material to be used. The survey will be conducted in 5 communes located in different agroecologic zones within Benin Republic. We are going to collect demographic data, farmers' preferred grain types, their pesticide use practices, and samples of these crops, maize and legume grain from intercrop fields are going to be collected from farmers. All samples that will be collected from farmers will be analyzed in the laboratory for pesticide residues and aflatoxin. All the data analysis is going to be carried out with our studio. As an expected outcome result for this work, we expect a list of our aim that we are expecting to as an outcoming from this work are: first of all, the identification of pesticide and aflatoxin residue in maize, groundnut, and cowpea. Secondly, the assessment of the impact of soil and agronomy practices on pesticide persistence. We also wish to have the evaluation of application methods, storage conditions, and potential risks of contamination. Also, we aim to test an integrated pest management solutions, as for example the use of aflasafe, a biological control solution, will be evaluated for its effectiveness in reducing aflatoxin in these crops. At the end, we wish to assess the economic benefits of adopting safer integrated management practices. So far, we have organized focus group discussion with key local actors to understand current farming and pesticide practices in some areas in South Benin Republic. This work is still ongoing. As a conclusion, this study will contribute to safer food systems by identifying contamination risks and promoting sustainable management. We cannot end this presentation without giving a thanks to the Food Safety for Africa, the European Union, and the International Institute for Tropical Agriculture, which are funding and support our work. We also say a great thanks toward the team supervision. Thank you so much.
Hello, distinguished ladies and gentlemen. My name is Dua Dafe, a student from Egerton University, Department of Agricultural Economics and Agribusiness, Kenya, East Africa. On behalf of my supervisors, Professor George Our and Professor Paul Kimurtu, I conducted a research on aflatoxin inhibiting technologies on groundnut in the Elgeyo Marakwet and Baringo counties, Kenya. As we all know, aflatoxin contamination is causing an alarming situation globally, causing many health complications in both human and animals. It also retards the immune system, causing stunted growth in children. It also causes liver and kidney cancer. It leads to low quality of groundnuts and its productivity, which eventually led to economic losses to smallholder farmers in African continent, in which Kenya is not an exception. The problem requires concerted efforts to devise potential strategies to overcome aflatoxin contamination in food crops, especially groundnuts. This will ensure access to premium markets by our smallholder farmers and safe and quality food available to the world population to feed. The vision is a safe groundnut is equals to healthy population and thriving economies. The power of aflatoxin inhibiting technologies is also boosting groundnut productivity. Thank you very much on behalf of SESAM and Food Safety for Africa Project. Thank you so much for your time.
Happy World Food Safety Day. I'm Sylvia Batia-Amini, a doctoral researcher at the Department of Nutrition and Food Science, and also an assistant research scientist at the Science and Technology Policy Research Institute of the Council for Scientific and Industrial Research. I'm affiliated to the Food Safety for Africa project. My research tackles one of Ghana's silent food safety threats, which is aflatoxins in groundnuts. Groundnuts are more than just a staple food in Ghana. They are a source of livelihood for me. But hidden in this nutritious crop is a serious danger, which is aflatoxins. And these aflatoxins are toxic compounds from fungi that thrive under poor post-harvest conditions, especially in informal markets where safety measures are minimal. Under the Food Safety for Africa project, my research, which is titled Risk Reduction Capacity of Existing Aflatoxin Mitigation Methods for the Groundnut Value Chain in Ghana, dives deep into how effective current strategies such as drying with tarpaulins and proper storage are in reducing aflatoxin contamination. So far, I have worked with over 800 value chain actors, including farmers, traders, processors, and consumers across Wild West and in Kwanzaa South districts through interviews, focus groups, and then still working towards lab testing. And here's what we are finding so far. This is what I've found. Aflatoxin awareness is still very low, especially among the farmers and the traders, as well as the processors and consumers. And while some farmers are adopting safer drying practices, many are still held back as a result of costs and then structural constraints. This research highlights the urgent need to scale up training and also improve access to affordable drying technologies. It also highlights the need to tailor interventions to gender and location for greater adoption. There's a need also to strengthen regulatory support, especially in the informal sector. As we mark this year's Food Safety Day themed Food Safety Science in Action, I'm proud to be part of the movement putting science into action to protect health and livelihoods. Let's keep food safe for everyone. Happy World Food Safety Day. Thank you.
Good day, everyone. I am Adam Douglas, a postgraduate student in the Department of Food Science and Technology at the Kwame Nkrumah University of Science and Technology, KNUST, Ghana. I am currently working with Professor Ogan Imba and Professor Meza at McGill University as part of a collaborative project. Today, I am pleased to share my research, which is part of the Food Safety for Africa project titled Reduction of Pesticide Use in Grain Storage Using Hermetic Bags such as PICS bags. Across many developing countries, including Ghana, the issue of post-harvest losses in grains, especially maize and groundnut, remains a major challenge. One significant contributor to these losses is insect infestation during storage, leading to both quantity and quality deterioration. To mitigate this, farmers often rely heavily on synthetic pesticides, many of which are not only misapplied but also harmful to human health and the environment. To protect consumers and ecosystems, there is a need to reduce pesticide use. Reducing pesticide use through better storage methods like hermetic bags can help lower harmful residues in food and protect the environment. Storage solutions such as Purdue Improved Crop Storage, that is the PICS bags, is essential to improve food safety and promote responsible, sustainable practices in storing maize and groundnut. This technology can improve food safety, especially in smallholder farming systems, and support sustainable agricultural practices. The objectives of this study are to evaluate the effectiveness of hermetic bags in controlling pests without pesticides, to compare grain quality and pesticide residues between hermetic and traditional storage systems, to collect baseline data on pesticide use, storage practices, and farmer awareness. A baseline survey was conducted to gather baseline data on pesticide residue risk awareness and management practices along the grain value chain, focusing on pesticides use, and residues. The survey targeted stakeholders in grain handling, storage, and distribution to assess their knowledge and practices. Key findings revealed critical gaps. Many respondents were unfamiliar with pesticide regulations and lacked confidence in complying with maximum residue limits. They often use synthetic pesticides manually, discarded grains if residue exceed limits, and rely on government agencies for updates, yet awareness remained low. Preliminary results showed only 20% of respondents had adequate knowledge of pesticide usage. This raises concerns about MRL, which is the maximum residue limit compliance, as improper pesticide application could lead to unsafe residues in food, impacting public health and trade. The study is expected to demonstrate that hermetic storage can significantly reduce the need for chemical pesticides, improve the safety and quality of stored grains, and provide a sustainable and scalable solution for smallholder farmers. To conclude, this research highlights a critical gap in safe storage practices among smallholder farmers in Ghana. From the baseline survey, it was clear that awareness on pesticide use and residue risk is very low. Only about 20% of respondents had good knowledge. This raises serious concerns about the potential for exceeding safe limits of pesticide residues in grains consumed by the public. With the experimental setup now complete and ready to commence, this research is well positioned to generate evidence that can support safer storage practices, improve public health outcomes, and inform relevant policy in Ghana and the wider regions. Thank you.
Good day, everyone. My name is Folashade Oladiti, a master's student at the University of Ibadan and a research fellow at the International Institute of Tropical Agriculture. Anytime I see people spray their food items along the roadside or openly display them in the marketplace, a lot of questions run through my mind about their safety. This research, funded by the European Union via the Food Safety for Africa project, has given me the opportunity to have answers to these questions. The title of my poster presentation is Data Generation of the Safety of Yam, Cassava and Plantain Products, sampled from the informal sector in Oyo State. Yam, cassava and plantain are important food staples in Nigeria as they contain a good source of energy and they are easily cultivated. They are mainly produced and processed in the informal sector. However, during production and processing, if not handled well, food contaminants such as mycotoxins, toxigenic fungi, and pesticide residue may creep in. These food contaminants are known to pose huge risk to public health. The samples obtained in this study were from roadside, covered surfaces, and open markets. Here is cassava sample, plantain samples, and yam samples. The samples were then subjected to microbiological and chemical analysis. The results from the microbiological analysis were 9 fungi genera, and they include Aspergillus, Absidia, Cholectotrichum, Fusarium, Epicoccum, Rhizopus, Mucor, Penicillium, and yeast, as seen in figure 3. The aflatoxin analysis showed a high concentration of aflatoxin across value chain, as seen in figure 4, but plantain samples from covered surfaces had the highest level of aflatoxin concentration. This indicates that processors may process their produce suboptimally. The pesticide residue analysis result showed emamectin benzoate as the most prevalent pesticide residue out of the 9 pesticide residue detected in the samples, as seen in figure 5. However, cassava had the highest concentration of emamectin benzoate out of the 3 crops. This indicates that or suggests that informal actors may prefer emamectin benzoate in the controlling of pests. In conclusion, the presence of these food contaminants indicates a need to increase awareness about the hazard they pose and methods of mitigating them, such as integrated pest management and good pre-harvest and post-harvest agricultural practices. There is also need to provide shared infrastructure facilities for informal sector actors to be able to process their products optimally. I would like to acknowledge the European Union for funding this project through the Food Safety for Africa project and the International Institute of Tropical Agriculture for the research fellowship awarded to me. Thank you.
Happy World Food Safety Day. My name is Kwame Epi. I'm a doctoral student with the Information Technology Group at Wageningen University and Research in the Netherlands. I present today an overview of my doctoral research project, which is titled Governance and Architecture of Digital Ecosystems for Food Safety in Africa. This project is part of a larger Food Safety for Africa project funded by the European Commission. The issues at stake here stem from the realization that food safety risks, including mycotoxins, microbial risks, and aflatoxins and lice, present critical challenges across Africa. This impacts public health and agricultural exports. Many countries, and in fact the African Union, have put in place laws and policies to address food safety risks. But these measures have, however, yielded very little results. And successful digital systems such as the EU's Rapid Alert for Food and Feed and the United States Import Behavior Report highlights the effectiveness of coordinated digital tools in monitoring and managing food safety risks. Now, Africa lacks digital systems and technologies which have successfully been used in other parts of the world to address these kind of challenges. Africa has fragmented data collection and sharing systems and has yet to realize coordinated digital food safety systems. Such systems comprise databases and platforms for gathering and sharing food safety information. This research recognizes that an important gap in the literature is the lack of understanding of the current digital food safety platforms, their interdependencies and architecture. And therefore, we put together this design-oriented research that aims to model the current food safety information systems, analyze how they operate, identify their limitations, and then propose a digital ecosystem architecture based on interviews and use case studies conducted in the context of the EU-funded Food Safety for Africa projects. The project's objectives include assessing the current monitoring systems, defining components of a digital ecosystem, and then evaluating an AI-based knowledge platform that is being developed and used within the project. By addressing these priorities, the study contributes to public health, trade competitiveness, and sustainable development across Africa.
Hello everyone, my name is William Oforiapel. I am a PhD student at the Kwame Nkrumah University of Science and Technology and also currently working on the Food Safety for Africa project with Doctors Ogan Emba and Ebenezer Meza Kofi of the McGill University in Canada. My presentation will be addressing knowledge gaps in aflatoxins in Ghana by advancing inclusive education for food safety in the informal sector. Food safety challenges, especially in low and middle income countries, are governed or driven by three gaps. First, in infrastructure, second, in awareness, and third, in regulations. Aflatoxin is a secondary metabolite produced by fungus and is responsible for avoidable deaths and health impairment in Africa and in Asia. It affects more than a quarter of the world's staple foods, especially maize and groundnuts. The informal sector is a key player in the handling and trade of these staple foods, which are prone to aflatoxin. Currently, the informal sector handles over 70% of the cereal value chain in developing countries. The informal sector still remains a very key area and a potential hotspot when it comes to food safety within the cereal value chain. A cross-sectional survey was conducted using structured questionnaires to assess the knowledge, the attitudes, and practices of stakeholders in the cereal grain value chain in 3 major regions in Ghana, namely the Ashanti region, the Bono region, and the Northern region. This was done to ascertain and to understand the real situation on the ground in the informal sector in Ghana. Results indicates that majority of the stakeholders were below the ages of 50. Also, most of the stakeholders we interviewed had no formal education. And it was also realized that the informal sector is very dynamic, where we have some of the stakeholders operating their businesses in the open market, in market shops, also on mobile carts. 63% of the respondents had heard or were aware of aflatoxins. When asked about the effectiveness of past aflatoxin awareness campaign, less than 30% responded in the affirmative. 51% of the respondents were not aware of the health implications of aflatoxins. However, more than 70% were aware of the economic impact of aflatoxins on their business. 100% of the respondents had no personal kits or equipment to test for aflatoxins in their day-to-day business. When asked about access to cheap testing solutions, only 2% responded in the affirmative to that question. However, 2% indicated they have had some level of experience with regulatory testing of aflatoxins. It was also noted that about 97% of the respondents were not aware of the legal limit for aflatoxins in food and food products. In summary, the result indicates that aflatoxin awareness within the informal sector is very low. And this is heightened by the lack of access to cheap and affordable testing solutions. There is therefore the need to equip and empower the stakeholders in the informal sector with actionable solutions. Some of these proposed solutions are: 1, a nationwide inclusive education and campaign on aflatoxin and its risk using the bottom-up strategy, where the informal sector becomes the first line of defense in managing aflatoxin risk and exposure. 2, the materials and the mode of education should be culturally and locally accepted by the stakeholders in the informal sector. Thirdly, everyone in the value chain in the informal sector needs to be engaged in both developing the manuals and also in the training and empowerment with the knowledge to fight against aflatoxin contamination. Last but not the least, there is also the need to prevent the recirculation of contaminated aflatoxin products into the value chain by repurposing these contaminated foods into high protein feed using insect larvae as bioconversion agents. Currently, there is a lab set up in Ghana trying to assess 2 different species of insect larvae in this regard. Doing this bioconversion of the contaminated foods provides an avenue to convert waste into something that is of value. It does not only reduce the level of aflatoxin exposure in the community, but it also helps to produce high protein animal feed that can be used for feeding within the animal husbandry space. This approach aligns with the Sustainable Development Goals, which is number 2, zero hunger, number 3, good health, and number 12, responsible consumption, and number 13, climate action. In conclusion, the informal sector still remains a crucial role to food safety challenges and solutions. Education alone is not enough. There should be structural interventions needed within the informal sector to help manage aflatoxin contamination and risk. There's also the need to provide solutions to potential gender inequity and inequality when it comes to access to education. Knowledge and innovation must go hand in hand, especially within the informal sector, where the stakeholders are empowered to take ownership of both the knowledge and the innovation in order to safeguard against aflatoxin contamination and food safety issues in general. I'll end with a quote by the Food and Agriculture Organization. Food safety is everyone's business. Innovation for resilience starts at the most vulnerable point, which is the informal sector. Thank you so much for the time, and thank you so much for your attention.